All right, so let's look at the first one. Did you guys go over this question last week? Is there anyone remember?
I don't think so.
Okay, so let's just work on this one, and I will give you guys about 2 or 3 minutes. All right, so let's look at this problem. So we're asking the probability of getting more heads than tails on 4 tosses of a fire coin. So if we just apply the definition of a probability, which we can first denote as to be the sample space. And then let E just be the event where we're getting more heads than tails. All right, so what would be our possibilities that or what would be our outcomes for N of E?
2 to the 4th. Oh, sorry. That's for S.
Yeah, so for the sample space, that would be 2 to the 4th. And yeah, and what about the event?
would it be 4 choose 4 and then plus 3 choose 4?
3 choose 4 or 4 choose 3?
Oh, 4 choose 3. Yes.
Yeah. All right. Yep. So that's the same as 4 choose 0 plus 4 choose 1. So so for the sample space where we have 4 tosses of a furry coin, for each toss we have 2 possibilities. That's why you have like 2 to the 4th as your sample space, and where we have the 4 choose 4 and 4 choose 3, you can think of that as 4 choose 4 is we have 4 we get 4 heads, and 4 choose 3 is that we get 3 heads and 1 tail. So this with calculation that should be, well, that should be 1 plus 4 and over 16, and that's 5 over 16. Questions? All right. So the next problem is an expectation. So we have we have a game winning with the probability of 3/5, and then we're asking about like what will be the average length of the best of 5 series between these two teams. We'll give you guys about 3 or 4 minutes to work on this one. Okay, so have you guys went go over this question last week from last week's discussion?
I don't remember doing it.
Okay, yeah. So yeah, I will give you guys 1 more minute, and then we can work on this one together. All right, so anyone wants to share the solution? You can also type in the chat if you have like at least figure out like the main steps you wanted to you want to do. So I guess you want to simplify down to the just the combinatorics. That's fine. So if you have something like 5, which is in the form of factorials, like 5 factors over 2 factors, and over 3 factors, that is fine. You can just leave it this way.
So I started the problem just by enumerating the possible outcomes for the games.
Well, so you want to think about like what are the different cases that you can actually have like the number of games like played until one team has like won 3 games. So what could be your cases?
License for the
3, 4, 5. Oh,
Uh-huh.
sorry, Kristen.
Go ahead, Dane. We can't hear you very well though.
Yeah, I heard like something 3, 4, and 5. Yep, so that's what we need. So we want to make sure that the number of games like played until one team has won 3 games. So which we must have so our case can be separated that as when we have a length of a best 5 series as 3 and a length of 4 and a length of 5. So so what's going to be our probability of when x is equal to 5 when x is equal to 3? Looks like we have something in the chat. Okay, 3/5 to the third. So actually, the probability right here, x, represent that the number of games in the series that have values of 3, 4, and 5, where the probability when x equal to 3 is actually the probability of you want to calculate on both sides, where the 3/5 to the third is only the probability when we base on win the game. So what you want to have here is 3/5 to the third and plus 2/5 to the third. Because right here we're actually asking about the average length of a best of 5 series. We're not asking about like the average length of like the basin gonna win the this game. So we want to find out on both sides. or we want to count on both sides, like the probability when the length is 3. And I believe with some math calculation, this should give you, see, that's 27 and plus 8. And that's, what is it? 125. All right, so we have 35 over 125. And what about the probability when x equals to 4? Yeah, 7 over 25. But let's just keep that because we want to eventually find out the average length. So we might, so we don't have to simplify right now.
So to find this next step, the x equals 4, is there an easier way than just enumerating all the possibilities and finding it that way? So I just made like a giant tree and it takes forever.
Oh, so just think about like two sides, like when for like just for based on wins the game, like it has like probability of 3 over 5, right? And the length, we know the length is 4. And then we know like if Basin wants to win the game, it has to win 3 games. So how can you choose that 3 games?
Oh, right. You choose 2 from the first 3 games, right? Because they have to win the last game.
Well, I think, let me see. Yes, that's right. Yeah. So you want to choose 2 from the first 3. And then it has to win the last game. Yeah, that's correct. So you will need to use 3 choose 2. And then that's only give you like the different combinations of like which games basically gonna win. And then you also want to time that with the probability.
So would that be 3? Oh, sorry.
Yeah, go ahead. Yeah.
3/5 cubed times 2/5.
Exactly. Or yeah, 2/5. And then for the other one, it should be like pretty similar. You still want to do 3 choose 2 and then times, this time should be 2/5 cubed and times 3/5. All right. And what about the probability when x equals to 5? So there are actually 2 ways to do that to find out when the probability of when x equals 5. You can directly use the rule of complement, which you can just use 1 minus the probability x equals to 3 and minus the probability of x equals to 4. Since these 3 probabilities are the only choices to actually have a like best of 5 series, So you can do this as long as you believe you got the first two part correct. And also you can just find out when the probability of x equal to 5 directly as we did for the first two. Which you will then first find out like the how many combinations I can choose from this 5 series. And then just times the probability where it's still going to be 3/5 cubed times 2/5 squared. And then the other part will be 2/5 cubed and times 3/5 squared. Yeah, so let's just write this out. Like I said, so you will have, so you still want to make sure that you want to win 3 games. So that will give you 3/5 cubed and then times 2/5 squared. And what about the combinations?
Or choose 3.
Yeah, so for, well, let me see. Is it 4 choose 3? So you want to make sure that so we have like a team wins the game when it had, so we want to make sure like one team has won 3 games. So we would actually probably need to make sure that that's 4 choose 2 instead. Because if you do 4 choose 3, that basically means that team already won. Yeah, that's right. So we just know like the last game. Yeah, so that should be 4 choose 2. Where we have total 5 games, and we know like Bison has to win the last game. So all we want to choose is that like which 2 games the team gonna win. So we just want to do 4 choose 2. So it should be similar for the other part. It's still going to be 4 choose 2 and times 2/5 cubed and times 3/5 squared. And this two, I believe, should be the same. It has to be the same. Otherwise, there must be some mistake. All right, any questions so far? Okay, so how are we gonna find out the average length of a best of 5 series?
Need to sum the product of the outcome and the probability of the outcome for each outcome.
So we actually have the formula for these average, or we just use the word the expectation. where we're just going to take the actual length times the probability that when x is equal to 3, and then plus 4 times when x is equal to 4, and then plus 5 times when the probability that x is equal to 5. And this will give you the average length of a best 5 series. So you can just think about this as it's kind of similar to the weighted average, where each probability basically means that like how important like it is playing in this calculation. And also you can interpret this expectation as like the more likely length of the best 5 series will show up. So this one should equal to, if you just do all the calculations, this one actually equal to 4.06. So roughly around four games. All right. So, okay, so if there's no question, I'm just gonna move on to the next one. For a question like that, I believe you can just write to the point like this. And then for furthermore, you can probably just substitute what do you have for the probability x equal to 3 and x equal to 4 and x equal to 5. That should be enough. And then if on the quiz, if she really wants you guys to write out the final answer, that would probably be some real simple like calculation, like yeah. So it would be like easier for you guys to calculate it without using a calculator. Otherwise, you can just leave it this way. Okay. Let's see the next one. So it's a probability on dice. So right now we have a pair of 6-sided regular dice are rolled, and then we want to find out the probability that either, or which means at least one die shows a 5, or the dice sum to 8. So think about the pair of 6-sided regular dice as 2 different dice, basically. And then think about like which strategy you want to use. I will give you guys some time to work on this one. All right, so let's look at this problem. How would you want to solve this one? So right here, we seem to have like two events involved here. Where let's first denote some events. So let E1 be the event that at least one die shows a 5. And then the other event would be let E2 be the event that the die sum to 8. All right, and then so the question asks like either one die shows a 5 or the die sum to 8. So the way we're going to write out this probability should be E1, the probability of E1 or E2. And then what should I put on the right hand side? Is it probability E1 plus probability of E2 or something else?
We want to consider an event where both occur.
So you will have probability of E1 and then plus probability of E2. And then you want to subtract like the part where they occur at the same time. Which has I'm just gonna use the intersection. It's the same as the end. And why is that? Because E1 and E2 are, what's the word I'm looking for?
Is it not disjoint?
Yep, exactly. So they're not disjoint. That's why we need to subtract the overlap part. Okay, so let's just look at this separately. So the probability of E1. Just by definition, we have this. And what should be our sample space? N of S. So like just treat this pair of dice as different two dice. Oh, yep. So it's just gonna be 6 squared. And then what about N of E, where at least one die shows a 5?
11.
Do you want to explain like how you get how you got the 11?
So what I did is for the first dice, I considered the probability that it rolls a 5 and the other die rolls any number but 5. And then that technically occurs twice for either die. And then you add the event where both occur.
Yep, exactly. I guess that's probably like the easiest way like I can think of, just by directly considering like two different cases and then just add both of them when they both are 5. So this will give you 11. And that's 11 over 36. And what about probability of E2? So I guess for the dice problem, or for just for this part, you can actually just count like how many pairs are there, where the sum is 8. So if we just think about all the possibilities, it should actually give you 5 outcomes. All right, and 5 over 36, that should be your probability of E2. And then now we're still missing the probability of E1 and E2. And what's going to be the probability of that?
Is it 2 over 36?
Exactly. And what are the 2 outcomes? So we should be 3, 5, and 5, 3. Yep, and then just by substituting all those numbers in, we should get 11 over 36 plus 5 over 36 and minus 2 over 36. And this should give you 14 over 36, and that's 7 over 18. Any question? All right, let's look at next one. So here's another expected value problem. So I will give you guys some time to work on part A first. All right, so let's talk about this one since we don't have much time left. So we have a casino game where a player first pays $10, and then the player wants to toss a die 3 times, where you would get $10 back for the first die that shows a 6, and additional $15 for the second die shows 6, and additional $20 for the third die shows 6. And the part I asked, like, what is the expected amount of money the player will win playing the game one time? So you know that it's another question on expectation. So what we need to do first is to find out the probability for different cases first. So what can be our cases in this problem?
Seeing 1, 2, or 3 sixes.
Yep. All right, if we just think about the probability of the prayer only have a 1/6, what's going to be the probability of that? So you have a die that you want to toast a die 3 times. And then what's going to be the probability that you only have 1/6? So we have 3 over 6 cubed. So I believe the sample space should be 6 cubed, but do you want to kind of explain like where you get the 3? Yeah, 3 dice. So 3 dice basically just means like probably the first die shows a 6, and probably the second die shows a 6, and probably or probably the first toast shows a 6 and the second toast shows a 6, or the third toast shows a 6. In that case, you also want to count the part where it doesn't show a 6. Where you actually need is the 3 choose 1, which is actually the same as your 3. At your 3 toasts. And then what you want to count is that you also want to count the other 2 toasts where now you only have 5 choices left for each of the other 2 toasts. Oh, oops, that should be 6 cubed. And then that's your probability of getting 1/6. And what about the probability of getting 2/6? So another way to think about this 1 times 5 and 5 could be that like there are actually 3 ways to choose this one, and you also want to count for the other 2 parts, like which number you chose for the other 2 times. So for the probability when you have 2/6, you would just need to do 3 choose 2. And then this should be 1 times 1 times 5 over 6 cubed. All right, and similar for 3/6, which should give you only 1 outcomes. And then just for the expected amount of money, as always, you just apply the expectation equation where for 1/6 you can get $10, and for 2/6 you can get 15. And for 3/6 you can get $20. All right, and if you just do the math, it will give you it should give you a number around 5.4 $5.42. And that is like the average amount of money the player will win playing the game. So do we not subtract the $10? Well, so I think this 5.42 only means like the when you did account for the $10, you can actually use the 5.42 minus $10, and that's actually like the actual amount of money the player will win. Which in other words, the average amount of money the player basically will lose some money. Yeah, but you will just minus $10 after you calculate the expected amount of money.
Can you hear me okay?
Yep.
Okay. I thought that if we got 2 6s, you would get $10 for the first 6, but then an additional 15 since we had a second one show up. So that would make $25 in total. And then a similar type of logic would hold for 3 6s, which gives the total 45.
Yeah, so I think let me see. I think the way the expectation is being calculated already account for the part where let me see. So I believe the expectation part will actually in count where let me reshare the screen. I'm not sure why it's not sharing. So I think the way you're thinking about this as like the probability of getting 2 6, where if the player actually got 2 6, you will get $25. But the way we're calculating this is actually separating them because I believe the expectation right here, the way we're calculating this is actually counting for the part where so this number is actually is actually like the more likely value you will get when the player actually playing the game one time. So you probably will get 5.42. So it's like the expected amount of money the player will win, but it's not like the actual money you're gonna win. All right, so we're already over time. So if you don't have any other question, you're free to leave. If you have like any if you still have like doubts on this one, you can stay and we can talk about this.